Good morning, everyone. My name is Donato, and my supervisors are Rano Cavallaro and Andrea Cini. My PhD title is Scalable Reduced Order Optimization Framework for Composite Aerospace Structure. And in a few words, I'm developing a tool that will be used in the optimization in the pre-design an aircraft with an high-order model with exact sensitive to be used with a gradient-based optimization, have the possibility after to scale the workflow of aeroelasticity and GP models. So the pressure of the last year is the clean aviation, and they it was to reduce the emission, to reduce the emission, the consumption of fuel. So they push to have a lighter innovative structure. So means that we want a reduction mass of the aircraft. One of the composite material come close to us because they help to to have a reduction of the mass, but increase the design space because they introduce the anisotropy, the stacking sequence, the coupling effect, all the stuff. So the main goal is to have the big problem is that we don't want only one analysis, a correct one analysis, but we want to have something that give to us something that can be repeatable and to be used for design of experiment or optimization loops. And the challenge, so it means, is that we want something that is accurate, but at the same time that is optimization readiness. So the motivation of my PhD is to create this physics-based tool that is cheaper, differentiable, robust, and scalable, that can be used in the optimization loops. The state of art nowadays, there are a few lines. One of these is the science and competitive optimization that trying to optimization of the stiffener paradigms with the stacking sequence, ply, oriental of the fiber and manufacture of it. And there are the high fidelity and low medium fidelity. High fidelity try to combine with in MDO, so with the CFD, aerostatic coupling, and the low medium fidelity in trying to use it to the early design space exploration. In parallel, there is a state of art of differentiable and surrogate models. They try to reduce the time consuming of early design space. And after there is a high order theory that refine beam hierarchy that you can have control of the fidelity of the structure. So these are the line that the current research that I just mentioned. They are powerful method, but the preliminary design workflow remain fragments. So for this reason, there are some gaps, like the high fidelity is accurate but is expensive. The low medium fidelity is efficient but oversimplified, especially with the problem of composite material that increase the design of experiment. And after there is, so we have a lot of design variable for the composite, and the surrogate model is don't have in this moment is useful, but I want to try to increase the surrogate model with the possibility to use an high order that I can change the fidelity of the structure, and I can achieve the surrogate model and train it more faster. So the main gap is that there isn't something that is simultaneously that high order model differentiable and optimization ready. So for this reason come a homemade code that is Augusto. There is a structural reduced order block for scalable preliminary composite design loops. Augusto is a CF++ code that I implement inside the final element Carrera unified formulation that you can see in the middle. They split the 3D model in two functions, one for the 1D and one to discretize the section with a 2D function. And after in this code, there is the join method that can help me with if I have a lot of design variable, don't give me more computational cost. And for this reason, there is an aggregation function, the Kreisel-Steinhauser, that helps me to have only one constraint and aggregation all the constraints that I want to compare, have the derivatives. For this reason, helped me the automation differentiation with the library of Codipack, because it helped me to have the exactly gradient of what I want, of the constraint. And there is MPI to parallelize all the code. So the code works that in the input I will put the parameterization of 3D structural dimension with all the complexity of composite materials, so the stacking sequence, the ply, the orientation, the thickness, all the input. And after, in the output, I will have the structural response, so the displacement, the stress, the strain, and the reverse mode derivatives that I will use to introduce inside a gradient-based interactive algorithm. And especially the Python works like Luca that is showing, shows that is our orchestrator that uses the Augusto like a library to answer to the question of Soler. And so Augusto is not just a solver, but is a framework designed to make structural model usable inside the optimization loop. What is Carrera unified formulation? That the structure, the final element that I use inside the Augusto. Carrera unified formulation is a generator of the mean structure theory that I can give a richness of the cross section by changing the function that I'm discussing the section. So it means that there is this function should be that discussing the section, the f tau, and I can use a different function and a different order of the function. So, for example, I can go to the low-order theory, like Aurora Bernoulli or Timoshenko likes. I can use a Taylor expansion that is a Taylor 1 that is Timoshenko-like. I can increase the order of the Taylor expansion of the section with the no limitation. And after, I can use a layer-wise discretization of the section to use the Lagrange expansion. So the Carrera unified formulation is the same. The potential of this one is that I have only one framework. I can change all the function of the order, and I can have a different structural theory. That can help me, especially with the optimization-oriented choice, because I don't need to have every time the highest order model everywhere, but I can choose which is the lowest order model that can capture the design-driven and I can use in the optimization. This is an example, a test case that I use in a conference. There is a stiffness panel with a 10 zeta stringer that is with a material orthotopic material with different inclination of angle of the fiber. And we can see that in the graph on the right, there is a different model, a 3D, 2D, the orange, the blue, and after there is the 1D with the Lagrange expansion and Taylor expansion. What they change in the points, every point is a different model that increase the number of the elements, so increase the degree, the number that you put, that you can see on the top of the point, that they are the degree of freedom of the model, so the complexity and the computational cost. For this reason, you can see on the left the runtime that increase with increase the element inside the model. And especially, I want to focus on these two. I take, and this graph, I have the normalized principal strain. This is a value of output of final element of the structure that you can see that I normalized referring with the 3D, the highest one. I take only these two of 2D and 1D to compare it because they are more or less the same runtime and the same line, more or less. And I achieved that the relative error with the reference of 3D, I have a 20% more or less for the 2D, and a 7% for my model that is a Taylor expansion with the order 3. And compare the 1D and 2D, you can see that the 1D model is 3.7 times faster than 2D, with a reduction of the degree of freedom of 99.4%. I use this model in the optimization. You can see that both of the model go in the same way that you can see on the graph on the right, that the orange, the green, and the blue, they are the thickness of the panel, the flange, and web of my model. And you can see they have more or less the same reduction and same direction of the optimization with a different interaction in different runtime. So the proof of concept that a reduced structural model can be accurate enough and can be used in optimization loop. The forward roadmap, they are the next conference. I will go with a different structure with the panel, box beam, a stiffness box beam, to have more or less the same result, compare which is the order that the layer one that I can use to have a good optimization and reduction of the time. I will increase the realism of my model because I will put the non-prismatic composite wing box, because in the moment I have only prismatic box element. I will create the next step, short step is the important one, is gonna be to create a different surrogate model. And I want to use the power of my tools that I can have a different fidelity, and I can have the gradient of the different design variable and the constraint. And I will create these 4 surrogate model that is GP, GP with a gradient, GP multi-fidelity, and GP with a gradient multi-fidelity. And do a time consuming to train it and to validate it, to have a new result. And the long-term extension is gonna be the error elasticity part that I will do a fluid structure interaction with optimization. The achievement, there are 2 conferences that I participated with the conference paper. There are AAA and ASN. And I'm writing the journal publication that have this tool, and I will apply with a benchmark that is a benchmark of Lightworks. And the next conference I will participate is ECOMAS on the end of July. These are all the bibliography that I use in this presentation, and thank you for the attention.